All right, it's been a busy 2 days, and so now we are at the final presentation for this session. So our next presentation is Navigating EMC Challenges in Automotive Ethernet Communication, Strategies for Mode Conversion Mitigation. Our speaker is Rohit Sharma from Molex. So please welcome Rohit. Sorry. There's two of you. Sorry, I missed that one. And it's Safal Sharma as well. So welcome to the two of you.
Thank you.
No problem.
Thank you, everyone. And we make sure that we make this more exciting. We have a last presentation. I'll make the thrill towards it. Thank you very much. Our presentation for today is the navigating the EMC challenges towards the automotive communication. As EMC being a very critical aspect, as we keep hearing, so it is very important to mitigate towards where we can in terms of various areas. So it will be presented by me, Rohit Sharma, and my colleague Safal Sharma over here. So let me get away from the presentation. Yeah, so here's the overall agenda that we're gonna have. So going from the background, like what we exactly want to achieve toward from the EMC perspective, or how we can do the mode conversion. And mode conversion significance, why mode conversion is very significant from the EMC perspective overall, right? And what design consideration we definitely need to follow to make sure how we can make the system more good to from the EMC prone. And some mitigation scenarios from our perspective, where the areas that can be seen towards how we can mitigate those areas, and some overall key takeaways. So from the background, as we know, single pair Ethernet currently enables a lot of this in-vehicle applications networking, such as ADAS, infotainment, right, and autonomous driving, V2X. So all these single pair Ethernet enables all these applications, but implementing these new protocols as we go higher and higher speed definitely leads to a lot of these challenges, because each of these protocols have to meet the EMC requirements, and that sometimes can be challenging, going from the vehicle architecture standpoint. If you go from the overall central domain toward the zonal, going from the OEM to OEM based upon the architecture, but the answer will remain the same to make sure we're meeting the EMC expectation around that. So that's the overall goal. So, and right now, automotive Ethernet channel is like a holistic system level operation, that every component around it have to, work together as a balanced system, so we can make this whole ecosystem work. So that consists of the MDI circuit to the MDI, here's the view toward the automotive Ethernet channel from the ECU to ECU as we look through, going from all the way from the FIDE, from the PCB to the MDI circuit, then the MDI header, going all to this toward the connectors and cables, and making sure each one of them have to work as a balanced system to make this whole ecosystem work. And to predict the performance basically from the component standpoint, S parameter being a very prime thing to monitor the performance across using the various parameters currently, like return loss, insertion loss, mode conversion, crosstalk being the prime ones being more used towards. So one of the key parameter that we believe is very important for significance wise is the mode conversion, because that can help us in indicating the impact on the EMI overall, because that parameter can let you to predict how our EMC will get impacted from the overall system perspective. And in this presentation, we're going to focus on some key elements like PCB, connector, and raw cable, which makes the lot of this critical part of this link segment that can lead to the overall balance towards the ecosystem to make the because as key component to each, they all have their own impact towards the mode conversion, and the balance on each component is very critical overall. But what is the mode conversion significance is? What is actually a mode conversion is? It is just a transformation when we inject the differential signal, some of the energies converts to the common. So, and that's gonna change again. So, and that impacts the overall signal to noise ratio of the system. That can lead to a lot of the EMC challenges. Because as much as more energy converts from the differential to common, that can lead to the mode conversions due to the if it's not properly balanced, it can lead to mode conversion. As you can see in these diagram right now, there is a direct current and a common mode current. And you can see from the impact standpoint, what is the radiated emission that can be generated from the common current versus the direct current right now. And that leads to the, more and more impact on the common current can lead to more and more magnitude of the emissions that can lead to your EMC challenges. And below here is the equations that shows towards like how these impact of this common and direct current has been calculated based upon the loop area of how this overall impact of radiation and how the magnitude of radiation can impact towards the common overall. And that's why it is very important to reduce your common mode current that can lower your unwanted radiated emissions, because the way we balance it out, it automatically can lead to your less impact on toward the mode conversion. So over here is an example of of EMC issues, because EMC issue can be lead up a lot of these GPS signal interruptions, infotainment interference, ECU disruptions, because all these EMC issues can lead to significant problems sometime. So and over here is the S parameter example, as you can see, that showing up like how an imbalance in a system can lead to a mode conversion issue that can lead to signal integrity and overall signal to noise ratio imbalance, and creating EMC challenges. So if you see in these S parameters right now, the two major parameters that we showed is the SCD11 transverse conversion loss and conversion transmission loss. Basically, you're looking at a 1.56 gig. There is a resonance that is happening due to the imbalance, and that leading the mode conversion high, and that is impacting the overall system at that particular frequencies. So any application certain that can run around that can be impacted, because you have a lot more emissions from the EMC standpoint coming from that resonance effect. So it is very important to consider every parameter towards like which can lead to the problems, and that's why it is very important to mitigate around those areas. So because as the Ethernet is, everything is very crucial towards to look. So like PCB optimization, connector layout, and raw cables consistency, as these are the major portion that covers a lot of this link segment, as very critical to important on every aspect. So from the PCB standpoint, like symmetry is very critical to make sure we have a proper symmetry around the layout. It is very critical to make sure that system is balanced around towards that, to avoid any unnecessary mode conversion raised due to imbalances. And the same thing in the connector pin layout, right? Making sure that all your pins are being properly terminated. You don't have any unterminated or not properly terminated pins that can act as another component that can lead to the imbalance, creating mode conversions. So improper terminations, like I said, can cause unpredictable behavior that can go and resonate to any frequencies. And same thing from the raw cable, because raw cable being a long low segment part of the link assembly is very critical to make sure they are have a proper construction around it. Improper construction can lead to, again, an imbalance scenario that can lead to EMC challenges around that. So that's why the overall is, let me go back. So going back to again, yeah. So to the careful consideration is a key factor that can minimize your mode conversion across the whole system. Now I will hand it over to my colleague Safal Sharma, so he can able to take you towards a little deeper dive towards how this mitigation scenario actually works and towards those different areas. So this is for slide change, and that's for the pointer over there. The bigger one.
Yeah, thanks Rohit. So Rohit spoke more about mode conversion significance on EMC, right? So I'll be talking more on, so the sources of mode conversion and from a board level, from a system level in a unique application, how to control that, right? So we know mode conversion always occurs in a practical circuit, right? So that is something I'll be covering. And so if you can see, how to go back. Okay, yeah, thanks. So if you can see this transmission line, right? So a coupled transmission line can be looked into two ways. One is I can see as a single-ended line having some coupling between them. So in that kind of situation, the signal propagating on that line is a purely single-ended signal, having some crosstalk between them. Now another way of looking into this kind of transmission line is like a differential pair. In that differential pair, two kind of signal can propagate or normally propagates. One is a differential signal that sees a differential impedance once it propagates down the line, and another one is a common signal that propagates seeing a common impedance, right? Now in any practical circuit, both the signal propagates. Even though my signal of interest is a differential signal, because of the geometry, because of various reasons, along with the differential signal, once differential signal propagates down the line, slowly the energy from differential signal gets converted to common signal. So at a particular point, I'll be having both differential signal and a common signal. So the energy is contained in a differential signal on the input side, but once it starts propagating on a transmission line, it starts slowly converting into a common signal. So this process is nothing but a mode conversion, and it can be reverse also. If I'm giving a common signal, it can come out as a differential signal, right? So this process always happens in a transmission line. In electromagnetics, this always happens. Now the point of concern is how to control that. I mean, we can't have pure differential signal. Always there will be some average value or DC value between the two lines, right? So how to control that? So there are different ways to control that. And also common mode, already Rohit spoke in the previous slide, common mode has to be taken very seriously. The reason being, normally common mode tend to produce more radiation. The reason is, in a common mode, the P and N both will be flowing in the same direction. The phase will be zero between the two lines. The net electric field coming from a common signal is the addition of the electric field components, right? So I'll be having a multiple electric field components. So the overall net electric field is addition in common mode, and it is a subtraction in differential signal. So that's why generally the common signal produces larger radiation compared to differential signal. So that's why it is very much critical and important to control that mode conversion, right? And so what are the ways to control that? So so in a practical circuit, right, as I told, always the occurrence happens. And the main reason why mode conversion happens is asymmetry. So I'll be having one line, I'll be having another line, P and N, right? So whatever this line has a property, be it a length, be it the magnitude, be it the phase, the another line has to see the same thing. It's like a Xerox. So we have to do a perfect Xerox of a P line to the N line. If anything changes, if any changes happens in a length, if any changes happens in a magnitude, the mode conversion will be there. I can have one line, P line, having a huge discontinuity. I can have a VI stub, I can have a huge impedance discontinuity. If I have a same impedance discontinuity on the other line, like a VI stub, mode conversion will be less. It's all about symmetry, nothing else. And we have to maintain the symmetry, right? So first thing is. Also second thing is in electromagnetics, always there is, so whenever signal propagates down a line, there will always be a displacement current going back to the source. And it kind of follows the least impedance path, right? So always there will be a voltage between the signal and the return. And in that voltage, electric field will be there, like positive and negative. So in that down the line, there will be a displacement current. So the overall loop, the propagation, the forward and the reverse, the overall loop also has to be less. We have to try to make the loop as less as possible. Otherwise, we can expect that circuit, that system to have some radiation. So in this particular scenario, right, the reason we have shown this area is, so you should understand, so this is a very critical area in a PCB design where we have a connector, where we have a cable, because connector would be connecting on this region, right? So signal would be propagating on a transmission line. So it will be propagating in a transmission line mode, like a TEM mode in a strip line. So once signal reaches this region, once it reaches this antipode region, the signal starts flowing into the VI, it starts coming up. So when it is flowing in a transmission line, the return will be below, normally in the below, right? P signal return on a P line coming towards the VIA, and on N line, return signal. So it will be, one will be clockwise, one will be anti-clockwise, going towards the VIA. Once it reaches the VIA, there will be a mode conversion. In a sense, from a transmission line TEM mode to a cavity mode. And the return signal starts distributing on a plane. So up to the transmission line, it will be below. Once it reaches the VIA, return current, displacement current gets distributed towards the plane. And there are very high chances of getting a cavity mode. And if you see in this slide here, right, so as we told, the signal has to see the same. So this is my P, let's say, this is the return of a P, and this is my N. So there is no VIA for a N. So P will see a constant signal and return, right? Even the capacitance and inductance between the two will be same, but in this region there is no return. So the displacement current starts searching for the least impedance path, and in that process, you will see current get distributed across the plane, and the overall loop will be more. And that is a major problem for mode conversion. Or in other sense, it might create an unwanted or accidental radiators in this kind of scenario. Yeah, so we kind of came up with this idea, and we built this board. So we did a simulation and we did a testing, right? So you can see one is so since there is a VIA is not there in one case, right? So it also affects the impedance. That's why there is a mode conversion in return loss. The return loss between P and N is different. And also on the insertion, on the transmission, the length is also different. Even though on the forward direction, length is same, but once the signal comes towards the source, because of the reverse propagation, there is a overall extra loop. So this is the simulated, and this is the testing result. This was pretty much on the board level, right? So what is good board, what is bad board. But normally in a single pair Ethernet or in a unique kind of application, so there won't be only PCB, right? There will be PCB, there will be connectors, signal will be flowing in a PCB. TEM mode, it goes to the VIA, goes to the cavity mode, again it sees a different structure, connector, again sees a different structure, cable. So a lot of changes happens in the propagation, right? So different electromagnetic field radiation, different. So always we have to look from a system level perspective, right? A good board can be a good board when we see only a PCB, but it can be a very bad board, even though on a board level it's a good board. When we see from a system level, so that's why for a connector cable system, it is very, very critical to see things from a system level. From a board level, if you only see it from a board level, a good design can be a very bad design. Oh, this. Okay, yeah. So this is a unique scenario, right? So, yeah, so in any conductor, right? So whenever time varying signal flows in a conductor, it has a tendency of converting that electrical time varying signal into electromagnetic waves. This is natural for any conductor. Now, if we want to have that electromagnetic waves propagating at a different, like orientation at a particular frequency, we can design that. We can orient that. We can do the geometry changes. Those are known as intentional radiators or an antenna. But many times we will be creating an unintentional radiator or an accidental radiator. And the main thing that drives or that creates this kind of accidental radiators are impedance mismatches from the source and the load. If a source is driven by a very low impedance, and if there is a very high impedance at the load, this is one of the key parameters of creating an accidental antenna, and that is what is happening in pin number 4. So on the PCB side, on the first one, right? Yeah, on the PCB side, yeah, this one. On the PCB side, it's connected to the ground. Typically a very low impedance, right? Ground has a low impedance. On the cable side, it's technically open, a very high impedance. So whenever signal is propagating from a PCB from a low to a high, it kind of comes back with 180-degree phase, and it starts radiating, right? And typically when the length of these conductors are integer multiple of a quarter wavelength, at those frequencies this behaves like a perfect antenna, like a perfect radiator at those frequencies. And one such frequencies, what we observed, what he was talking about, is at 1.6 gigahertz. That is the quarter wavelength resonate that is happening, right? And now how I will mitigate this? One thing is very simple: connect ground on the PCB side, put a ground or a drain wire on the cable side, done, problem solved. But in a single pair system, in a unique application, that might not allow me to do that, right? So in that situation, what to do? It might create a extra emission, right? So in that kind of situation, one thing is, since it is open on the far end, I can keep it open on the PCB side, so that this noise is not injected to the system, it is not going to the ground. So the condition of low impedance and high impedance is not met. So this is one technique, one idea to overcome this kind of scenario. And this kind of scenario definitely acts as an unintentional radiator. But also, let's say there is a radiator near me coming towards my system that is giving a electromagnetic field. This can pick up that field and inject it to the system also. So it is not only what is giving out, but what is giving in will also be affected by this kind of scenario. So that is what we have done in the next slide. Yeah. So we kind of did a simple simulation here. We created a 1 volts per meter electric field, right? That is K is the direction of propagation going towards the system, where I have an accidental antenna. Now, once it goes towards the system, we created a electric field monitor in our simulation platform. And in that particular region, basically in this particular region, because of which it is creating an accidental radiator, in that region, the noise picked up is more when it is grounded and when it is open. So when it is open, the noise that is picked up is less, but when it is grounded, the noise that has been picked up is more. That's because whatever it is seeing on the other end, same thing it has to see on the board end, right? Yeah, so we kind of created a board and we did a testing also. So as I said, in a unique application, like for example in a single channel Ethernet or similar any other application where only we have a one cable, and inside that cable bundle, let's say I have one pin as a drain and other two pin as a differential pair. So in that kind of application, what will I do with a pin 4? Because pin 4 is a part of a return path up to the PCB, right? It's giving a very good common mode performance on a board level. Very good design. It's like a coplanar transmission. But once I connect a connector that has only 3 pin connected on the cable side, where pin is open, even though it's a good design from a board level, even though it's a perfect, I won't tell perfect, but it's a design that is giving a very good performance when I'm looking from a board level, but in a system level, this will create a problem. And same thing, so you can see the simulation and testing result. So brown and the blue one, right? So already we have shown this in the second slide also. So the noise that has been picked up by this accidental radiator at a frequency which is 1.6 gigahertz, which is an integer multiple of a quarter wavelength of that frequency. So that has been mitigated. So that in the balanced one, we didn't see that in simulation. So same thing we tested, we created a board, we designed a board to prove our concept. And then you can see in this board, right? So pin 4 we kind of disconnected in our layout. So it helped us to mitigate this resonance occurring at 1.5 to 1.6 gigahertz. And we also did radiated emission testing and a simulation. So that I'll be showing in the next slide. So here we kind of created, so in the lab we kind of used a near field probe above the area of interest where the pin 4 is present, right? And this is the simulation. We kind of replicated the same thing in the simulation. So we created an antenna that replicates the near field probe. We try to maintain the same distance. And so left-hand side is the simulation result and right-hand side is the testing result. So balanced and imbalanced. That means with pin 4 connected to the ground and with pin 4 not connected to the ground. So not only in common mode, but we are seeing this difference in a radiated emission test also. And if you see the one in the top, right? So we also kind of created a field monitor here at a 1.6 gigahertz frequency. And at this particular location where pin 4 is there, you can see the electric field magnitude shoots up. It goes drastically up. So yeah, I mean, so yes, you can see. So a good board, a very good design can create a problem in a system level scenario. So that's why in this kind of application, it's always advised, it's always better to look from a system level perspective. Yeah, so now I'd like to hand over to Rohit to give his some comments on cable and conclusion. Thank you.
Yeah, thank you, Safal. So now we have seen from the PCB and connector perspective, but there's another piece that adds up towards this raw cable scenario, right? So here's a S parameter example showing up the imbalance in a raw cable can lead to the mode conversion, right? And that, so you can see, and that can be for various factors that improper construction can lead to, whether it's from the conductor concentricity, twist rate, or conductor balance, and etc. So in this one, you can see there's an example of conductor concentricity example showing up the, the core of the cable, one left side by being a balanced centered core versus the right side showing up the imbalanced core, where one of the conductor core is imbalanced across one-sided. So that can lead to the imbalance that can overall spike up the mode conversion, that can lead to the EMC challenges overall. So as you can see from the insertion loss and from the mode conversion, reflection and insertion, you can see how's this, being imbalanced, raising up the whole magnitude of the mode conversion, leading to an overall effect of the system, leading to a big EMC challenges. So that's why every component is critical to make sure they are properly balanced so we get overall system works as a balanced system to mitigate the EMC challenges. So the overall key takeaways from this side is like, okay, it is very necessary, right, to ensure the channel components like PCB, connector and cable, they are properly being balanced because they all have to operate as a system together to be, to work this automotive Ethernet to work on the system, right? And so that's why it's very important from every component aspect, because design imbalances can lead to increased mode conversion that can lead our EMC challenges overall. And it is very essential to examine each one of the component, as we have seen how each component can have its own impact around it mode conversion, getting the overall imbalance. So although we all know that it's very difficult to achieve a very interference-free system because it is not feasible, but we can always take some measures as overall, where we can mitigate it or balance it as quick as possible. So with that, that's the end. Thank you, everyone.
All right, thank you. And we'll open up the floor to questions. All right. If I wait long enough, somebody will go up and ask. There we go.
Hey, Rohit. Safal, thank you for the presentation. How likely do you think this will happen, or this effect could happen with shielded twisted pair, not an LVDS like the example that you showed? Is it possible to have that in STP?
Yes, so if so, I could give you from my side, like, and then I will let Safal to add up too. So yes, because it can happen because, like I said, it's all about the layout, right? It's where is STP or the other system or coax. It's all about how we are laying out the system and how we balancing every component around it. STP being the same thing with the cable. If the cable is not improper construction, can like example we have seen can lead to those mode conversion or from the PCB side or from the connector side, because technically regardless of which are being used, the proper symmetry, construction, those are very important, for the overall impact to consider. Yeah.
Yeah, I mean, so Gustavo, to your point, right? So until the condition for an accidental antenna is there, it won't go the problem, because the problem is happening because of pin 4 not being taken care on the cable side, right? So if you are using a shielded twisted pair or unshielded twisted pair, the problem is from the pin 4 getting not connected, so that there is a complete standing wave pattern generating on that. So because the signal is going back, so until that condition is there, doesn't matter whatever cable we use, there will be a problem. This is what our studies has shown us.
And one more question. Excuse me. What do you think is more important to have into account? A good balance on the cable side or a good balance on the PCB side?
So I think overall approach that we have shown, every place is important, not just like picking one side, because one component imbalance can lead to the overall system compromise. So that's why it is always important from each component perspective, as each component brings its own, things onto the table, that we have to work as an ecosystem towards it. So whether it's a PCB, connector, cable, or other component that can lead to that, everybody have to work together as a balanced system. Yeah.
Yeah, just to add one point, right? So correct, but sometimes since the chipset is from the PCB, right? So it will be switching continuously at some particular data rate. So little bit, some weightage has to be given on a good layout of a PCB, because normally the noise is injected from the PCB, which goes down the cable end. So PCB is also very critical, Gustavo.
Thank you.
Anyone else? All right. Last chance to ask questions for the whole event. All right, I think we're good. Thank you very much for the presentation. All right, well, that does bring us to the end of the agenda. So I did want to take the opportunity to express some thanks and make a few closing remarks. First of all, I wanted to thank Ford for being our host and sponsor, or our host for this year, and particularly Amrit for his leadership on the steering committee for the conference. Absolutely have to express our gratitude to all the sponsors and exhibitors that we have. Without them, they're what make this event a great success. Thank you to all who put in presentations. I mean, you only saw 15, 16 of the presenters here, but there were a lot of proposals for presentations. And so, not just to the presenters that you've seen the last 2 days, but, also thanks to those who put in the work to think up great ideas for the future. I think finding new and innovative ideas to be presented is always a big key. And so we appreciate everyone every year continuing to contribute like cutting edge information that is, of great benefit. So, and you can start to contribute for next year, which I'll mention in a second. Before I get to that, I did want to say thanks, of course, to the steering committee and program committee. I'm not sure there's that many in the room right now. I saw a couple of people. I see John's back there and Damon's back there. Haysom was here before. Yeah, so if you are on the steering committee or program committee, just please stand up and take a round of applause for all your hard work. That's a lot of meetings go into this. I have to extend a special thanks, particularly since she just walked in the room, Rosalinda, our project manager, who makes, I get to stand here and I get to be the face, but all the work, she's the one who does all the real work behind the scenes. And of course, Jen, who's working with her, she's from our IEEE Standards event team as well, who handles not only a lot of the logistics for the event, like working with the venue. She's also the one who runs the registration system, which sometimes I know drives people crazy, but it still does, it works. So again, thanks to Rosalind and Jen for making this a success on site this week as well. With that, this is sort of a lot of people have heard this, who they've talked to people and heard this, but next year we are going to be in France, in Toulouse. Same week in October, and our host company is Renault, this is actually kind of new in that in the past we would finish an event and then it's like, all right, where do we go next? So this year we actually were able to start planning ahead. So you can actually start putting it on your calendar for the middle of October next year. Nothing like a nice trip to France in the fall. Okay, and I'm trying to think if I've forgotten anyone. Rosalind, did I forget anybody to thank? Oh, well, thanks to the AV team in the back, and and everyone else who supported the event directly on site, and of course our a lot of the crew who helped with all the setups for all the exhibitors, and I think that is about it. If I forgot somebody important, I apologize, but just trying to do this off the top of my head. Again, I know how I forgot. All of you. Thank you so much for attending. We greatly appreciate your attendance year over year. We hope that all the information and the exhibits are beneficial, to what you're doing for the industry. And we look forward to seeing you at all our future events as well. So again, with that, we're going to wrap up, and thank you so much, and safe journeys home.
Fresh as the summer breeze. Keep me so much. I will take my hand.